All right, then. How are you today? So I have a feeling that we meet way too often this week. Become familiar with your faces. That's really good. How was your lunch? Good. Okay. So, all right. So, you ready to participate in some discussions? Well, I will not ask many things today. Yeah. What are we talking about here? I mean, in this course so far. Yeah.
Knowledge.
Knowledge. Yes, cool. But I mean, what is the focus of this week? Just to tune on just to be on the same page, to be sure that we are in the correct room, following the correct course.
Agents.
Agents, yeah, okay. Why do we need agents? Agents? Can we survive without agents? Well, yes, we do. But I mean, why do we need agents? What problem we try to, what technological problem we try to address here? Did you eat part for lunch? No? Um, you remember open distributed systems? So systems that technical systems that work in changing environments, systems that you cannot program by predefined algorithms, which need to react on changes in facts. So then that is a kind of opposite to writing a narrowly specialized program doing one thing. So when you as a programmer or architect design data structures based on the knowledge of your domain and hard code the processing. And then if something changes in your data model, then you need to do adjustments to your program, to the logic. And we want to, well, we talk about AI. I mean, so I mean, are evidences, we humans are evidences of uh, biological computing systems that are very adaptable. So we have, and seemingly, we have a kind of a universal routine or a universal engine that operates on facts about the world and relationship between facts. So again, so many things are not very clear about how exactly this is implemented in brain. Also, many things um, are understood. I mean, how different parts of the brain work in this respect. But what is clear is that we all possess a memory. Yeah, where we somehow store our facts and relations, and we always our mental process is about analyzing these facts and deriving new facts, and that's what we call reasoning or inference. Yes. And that's what we want to recreate here. I mean, in technical systems. And we started, and that is the reason for introducing agentic approach to design of software, where agents, I mean, amongst all possible types of agents, we are talking about intelligent agents. So they have this memory that can be populated with facts, with new knowledge, and decoupled processing, so the processing engine that operates on this memory. And all our actions are, I mean, we cannot do anything without consulting the memory. So without checking whether our next step, our next action, actually supported by memory. And yesterday we finished well, we started to talk more technically about this settings. and we focused on maybe the simplest way of analyzing or approaching creating such systems. We talked about logical agents. So the agents which inference is based on formal logic. So formal logic is a key word here. And uh, not any logic whatsoever, but again, maybe the simplest one of simplest ones, classical logics, which is predicate logic. So we live in the world where everything is binary. So things either exist or not. And we can put these things in the different logical relations using well-defined syntax and introducing semantics. So again, when you hear word semantic, people tend to misuse it in different contexts. So here it is assignment of meaning to variables. So that's as simple as that. So we have variables on the one hand, and we give it meaning. So what does it mean? So like in our scenario, if we go back a little bit, that one. Yeah. So we assign a symbol of a presence of thing, poison, a symbol P, and we say that symbol P is presence of poison. The same goes for percepts, so a smell in the neighboring cell. So, and this process is called semantic. Something which I didn't tell you, it is in the book, but I just want to highlight the ultimate importance of this word, because to a large extent, it's not fully resolved within AI in a systematic way. The grounding process. Did you hear about grounding process? Well, it's written here, but I mean, can you formulate it in your own words? What does it mean, grounding?
The agent takes, I guess, facts it already has and applies it onto the real world.
And what does it mean?
It tries to make a connection between what it knows and what it sees. I'm assuming.
Exactly. So, I mean, here uh, it's an interesting discussion. Let's drift a little bit towards this side. So one thing is to assign a symbol to a thing called, say, cat. But you need to connect it to a real perception of this phenomenon of a creature that has four legs, blah, 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 blah. So your grounding is about this bridge between the real world and the symbolic world. So basically, it's about representing or obtaining usable representations of concepts grounded or anchored to real world objects. A question to you. And again, so if you kind of read Introduction to Artificial Intelligence and you read about problem of grounding, so people normally say so there's two different camps. So one is, I mean, the more symbolic approach to AI. So I mentioned it in the first class, versus connectionist approach to AI. So pure symbolic approach is people see it as I mean, one of the shortcomings, serious problems is that by itself it is not grounded. At the same time, connectionists or neural networks guys, so they say I mean, this is the way to ground the concept. So basically, if you build a classifier, neural network-based classifier that, for example, analyzes pictures from a camera and outputs labels. So this is the grounding process. A question to you, ChatGPT, is it grounded? I mean, so now everybody said ChatGPT or I mean, like models, they are good candidates for artificial general intelligence. That's a strong claim. Is ChatGPT grounded or GPT models, LLMs, are they grounded? I mean, it's a kind of question without any without a single answer. So let's just think about it. If it's grounded, in what it is grounded? Well, it is partially grounded. It is grounded in one way or another. If you, I mean, they have this kind of combined modes where it can understand even, for example, pictures. So in principle, it can be grounded. However, I mean, that's what you see as a output from this model. The way how it is trained, the way how it is trained, and it is trained on texts. It is not grounded to the real world. So it is trained on purely on text. But again, so that's a very kind of little bit mind-bending discussion. But at the same time, it is grounded in the concepts defined by natural language. So we humans, I mean, in all the texts, so we give meaning to the symbols. So and in this way, so there is a kind of grounding on the conceptual level. But and again, so architecturally, so there is a possibility to link it to the perception system to be fully grounded. But so that's important thing when talking about reasoning in the context of real systems and agents operating in a real environment. So so the symbols should be grounded. So let me see what I have here. Yes. Right. So now let's recall what we stopped at yesterday. So we have the syntaxes, meaning that we can represent atomic concepts. We can build complex sentences, logical sentences, and can and on top of it we can give meaning to it. And we put these sentences in a database, which we call, or in a memory, which we call a knowledge base. So, what is a knowledge base, essentially? Again, so from the point of view of uh, agent, a particular agent. So, knowledge base. Uh, uh, Essentially, it's a equivalent. Oh, that's good comment, absolutely. Is a set of rules. Uh, rules. So everything can be seen as rules, even like atomic facts is still can be seen a rule, and the rule is so rules characterize variables and relation between them. So rules variables uh, and relations between them. So now, on the one hand, yes, we have this Boolean logic and stuff like that, but I just want to make a kind of quick transition from the engineering perspective. So, on the one hand, so we have a kind of our environment. And so this is a complex thing. So it has lots of variables and lots of relations between them. Um, and the only assumption we make that there is a logic in this environment. So I mean, so nothing happens randomly. We just haven't discovered this logic. So I mean, how the objects are situated, I mean, how they relate to different actions relate to each other. So we just discovered them all. All right. And then we have a knowledge base. So our agent, so this knowledge base. Well, let's have it as a bank, data bank. So it reflects a small portion of this environment, basically. Small portion of environment. And it does so by a set of non-contradictory rules. So rules are consistent. So, and there is a separate process in the reasoning which is responsible for checking consistency of rules. So they're like, but that's not part of propositional, but instead of consistent rules. Hmm. So, and we fill it with particular facts as we go. For propositional logic, for PL agents, so we assume that we have a universe with finite state of so it's a finite environment. So or it means that all symbols are known. So it's kind of a restricted case. All are known. We just so it's a finite universe. So it's a finite environment. Yes. And as such, since this is our main assumption, so we can enumerate all the variables. So we can uh, or we can enumerate all possible situations how variables can be assigned. Of assignment. Yes. So what does it mean? It means that uh, our knowledge base is essentially uh, a long list of possible assignments. So if we have our variables x1, x2, xi, xn, and so the meaning we gave that, for example, what is it? So here is our percept. So here is, for example, object. And then we also so what we do, we keep the rules in our knowledge base. So we have rule 1, rule 2, etc. Rule n. So these are the rules. So which describe the relations between these variables. And so we what we can do. So this is our knowledge base. So this is KB content. We can so since we have the finite number of symbols in our universe, so we can try all possible assignments to this symbols. So and since this is a Boolean case, so then we have 2 to the power of number of symbols combinations. So starting from false, false, blah blah blah, false to true, 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 true. And so for each case, we obviously can evaluate all the rules. And so here it can be like false, true, true, uh, and such. And what does it mean that our knowledge base support one or another outcome of computations? It means that all rules should agree on something. So all rules should be true. So well, essentially, you do logical AND of all rules. And basically, here it evaluates to false, etc., etc. But then uh, we have a hypothesis. And our hypothesis, we hypothesize about a particular value. So, for example, x I equals false. False. So, for example, so there is no poison in certain room. So, um, the inference then would be to locate this part of the knowledge base or of this through amongst all the possible assignments. So the place where you have zeros um, for your variable of interest, and check whether your knowledge base, so when evaluating rules, produces true, so that knowledge base supported. And again, so that corresponds to this notion of entailment. So in this case, uh, if uh, in all models where certain sentences true, the other model is also true. So then this other model entails the first one. Yeah, but let us again see it maybe on an example. So these are our rules, very, I mean, in a fast-forward manner, so we will not stay here for a long time. So here we are, and we registered that so we don't have any poison here. So that's we reflect as rule number one. And so then these rules 2 and 3 they appear because of well our assumption that about the environment that we feel smell only if there are objects containing poison in the neighboring cells. Uh, and in principle, you feel this, you create these rules for the entire universe. So it's a finite universe. You know uh, all possible places where it can be. So these generic rules you generate for all possible cells. But here we just showed the corresponding ones. Yes, and then so we also in this specific case we do not feel any smell in our cell, and maybe I mean when moving to cell two, so there we do feel smell. So that's our knowledge base. So then again, so the oh yeah, sorry. Our hypothesis would be that there so we want to move somewhere, and we've been here. It's a bad so we have a bad smell. So we want to make our next move. So we can return and say, okay, so we now test that, or maybe we are still here. So, but we want to say, is there poison in cell 1, 2? Well, you can formulate the hypothesis also for other cells, but just to exemplify. So we want to check whether we can go there, and before we get an answer from our knowledge base, we cannot do any move. So, and our knowledge base should support this hypothesis that there is no poison in this room. So it means that if so you need to find a place in your which is in your truth table, so describing all possible outcomes, um, which agree on that. So basically, I mean, you can verify that in only 3 cases, so P21 is false. So that is our hypothesis. So this hypothesis is true, and so all rules agree for this case, so that the knowledge base entails this hypothesis. So it means that we can go there, so we can conclude that there is no poison in there, so we can safely move. But so that was a technique, a reasoning technique called model checking. So you check extensively all possible models. A model is one instantiation of a world, if you remember from yesterday. And if you think about it, so I mean, so here we have a computational bottleneck. Uh, So on the one hand, to check a single model, so just to verify a single model, it's very clean, obviously. I mean, it's linear in M. On the other hand, if you want to find all models in which your hypothesis uh, is valid, then this situation is different. So you need to do a brute force search. So you need to check all possible outcomes to find whether the truth table satisfies your hypothesis. And obviously here, so we end up in a situation where, depending on I mean, the more variables we have, the more possibilities there will, the more entries in the truth table there will be. So, and it is actually, well, it grows exponentially. So it is, so it cannot be solved in a polynomial time. So, and here we come to, well, an interesting formulation of satisfiability checking problem, which is formulated is that is there some model or models that that entails a certain sentence. Let's face it. So basically, truth tables, as we have figured out, is not the most efficient way uh, of um, uh, of checking satisfiability. So there are other alternatives, and that's what we will be talking about today. So we will be talking about inference by theorem proving, or well, a general approach to solving SAT problems. So what is theorem proving? So now from theorem proving, uh, theorem proof. So if before we have so our knowledge base was truth table. So we transition to having it as a Boolean formula. So make it as Boolean formula. And well, I have already mentioned that uh, or indication that a knowledge base agrees on a certain statement is that all rules should hold. It should agree on that, and that means that we basically represent our knowledge base as conjunction of rules. R1, R2, Rn, so whatever rules we have. And the idea with theorem proving is, or the task is to find such assignment of variables to this formula, so that it is evaluated as true. So can we instantiate in B formula. Acknowledge that our hypothesis is supported. Um, so now again, so maybe to avoid a long discussion, so I intentionally said that not evaluates to true, but supported. So the SAT problem, so satisfiability problem, is a generic problem. So for any Boolean function, so any Boolean function with and or not implies, etc. So put together to find such assignments of variables that the function evaluates as true. So that's the satisfiability problem definition. In theorem proving, we do a proof by contradiction. So if we have a hypothesis, so we negate it and add it to the formula and see whether this construct is not satisfied. So it evaluates as false, or you can show that you cannot find such assignments of values that uh, or you can find, or you actually can find such assignments that evaluates the whole construct as true. So that's what we will do. So it will be we will do proof of so that in SAT Boolean Boolean formula evaluates as true. So inference. So negate hypothesis. So H. So you do KB and not H. So proof or proof not set. So SAT is satisfiability. Yes. And there are different ways of approaching solving this satisfiability problem. In either case, the first thing you need to do is like a major step, so main step towards solving SAT is to do what? Is to convert your formula, your Boolean formula, in a special form. Formula to what? And how? So I heard yesterday you talked about this form, this special form. So I just yes, exactly. So which is C and F. Uh, Uh, so conjunctive normal form, which essentially is a set of disjunction clauses. So you have your variables x1 should be or x 4 2 blah 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 and uh, and x4 or not x blah blah blah, etc. And you have conjunction of these terms. And we had example yesterday. I just scroll back a little bit here. So that's a way to convert a Boolean formula into a conjunctive normal form. So we have formula in this form, and then we apply this logical equivalence rules iteratively or recursively. And at the end, we convert this formula into this shape where we have the conjunctions of disjunctions. So we are happy. So in this form, we are ready for theorem proving. So before the break, I just want to kind of outline the main approaches for solving such problem. Main approach to solve a SAT problem. You can do it either by well, in either of two ways, or actually three ways. So you can do it. You can solve it either by something which is called conditioning, or resolution, or in a hybrid way. So basically, conditioning. So we start with conditioning. Is the way where you conditioning. So you pick a variable, pick a variable, and so assign true, assign it a value of true or false. Or let me split them. So you assign it a true. You simplify formula and evaluate, check if SAT. Then you do another assignment, false, and do the same, false, and simplify and check SAT. So that's how major SAT solvers approach the solving or checking satisfiability on a very high level. So after the break, we parse one simple example and also return to our knowledge base for a more concrete case. So let's take a break, 5 minutes.
Great. Excellent. 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 Det är som fast som gäller. Som får inte sådär. Jag ska någonting för det var för att inte visa. Men det där jag gjorde ett jättefint men jag minns inte vad. Det blir lite namn. Det var jättefint. Nej. Det är inte det är nej, det är fiction. Nej, det är allt. Det är allt. Men om den här? Nej, vad menar du? Om man är som en fond. Ja. Jag måste säga. Det är riktigt bra. Den får ja, nej. Ja, men jag har alltså den här. Ja.
Ni ska testa Remarkable. Den är otroligt bra, tycker jag. Det finns i det nya. Så det här är version 2. Så i 3:an det finns färger.
Colors.
New hardware. You mean? Yeah. You need.
You're dominated.
Yeah, but I mean, it feels like a paper.
There's like screen thing and it just feels like a paper.
That's a new hardware. Logic. But for this, you also need a new special stylus, right?
Special what?
Yeah, pen. So.
Well, yes. Yeah.
Well, it's more universal, yes. And you can do other things on it.
But it's nice that it integrates well.
Yeah, but yeah, indeed. But it also, I'm kind of dependent on their software, so there is no third-party software that integrates. But I mean, so far it works good.
Because I'm not sure. I don't think ours. Like we can live show it like that while we're writing. We can see each other's notes.
No, you can. I think you can do screencast, maybe.
Yeah, fully just through the iPad. Yeah, not the software itself.
No.
Yeah, that's true. Yeah.
So are we all set, or no? Are we missing anybody? Couple of people. So let's continue then. So we talk now about SAT solving by conditioning. And so in general, so for a given formula, you build a tree of conditions. So a binary tree of conditions. So as I said, you pick a variable x1. So you assign a value of true or false. So you evaluate. So you try to evaluate a function. If it goes immediately, fine. If not, so you take next variable x2, and so you try to assign true, false values here, and etc., until you reach the leaves. So where you have your x3, so maybe you end up with single one. Yeah, and so basically, this is for a satisfiability, a general satisfiability problem. You're just happy to find any instantiation that leads to true. But there can be many, of course. So let's trace a simple example. So example. So for example, we our formula will be f equals x1 or not x2 and x2 or x3. So this one. So let's trace it. So set.
So it would be example.
Yeah, I will. It was not probably a good idea to write it here, so I will write here. Yeah. No, x1. No, x2 and x2, x3. So this is our formula. Um, so first step. So set x1 to true. So what it will be? So true or not x2 or and x2 x3. So which boils down to what is it? Well, this whole thing becomes true, right? And um, and um, x2 or x3. And in order to make it true, so this must be true. So that must be true. But and now we evaluate whether it can be true, and of course it can be true if either x2 or x3 are true. So and it can be. So you basically set x2 to true, so check or x2 or x3 to true. So at the end, so we arrive to a possible assignment, and so we prove that. So it's that. That is fine. Um, But then again, so if you are interested in several possible solutions, so you continue doing that. So you set x1 to false, and then just skipping some steps. You get minus x or not x2 and x2 or x3. Yeah, so and here we have two cases. For x2 being true and x2 being false, uh, so this problem is unsat. And for initialization as false, it is set. So you can verify it. With this simple example, we see that there can be several assignments, and this is one of the ways uh, to check satisfiability. So now let's before returning to the slides, so there is an alternative, and normally this alternative is also used in the conditioning way of solving SAT. So alternative way of solving SAT. Way of solving SAT, which is solving by resolution. Resolution. So and basically for a resolution, you use the following observation. So if you have a clause which contains a variable and a negated variable, and another clause containing negated variable, so if we have this x and oh, and some other clause containing not x, then you can resolve it to a or b. Yeah, and this one is called resolvent. Resolve. Yes. So again, in our case, you have x1 or not. No, no, yeah, I used a different one. And x2 and the second clause, so that's C1. One. And the other one is not x1 or x3. X3. And then you also have some facts. So not, so that will be C2. So you have C3, which is not x2, and C4, not x3. So this is your CNF. So yeah, I mean, soon we will match it to our knowledge base. But I mean, so we have some relations and we have some statements, some factual statements. So the resolution is about applying the resolution rule. So the and in this case, we first resolve C1 and C3 into C5. And C5 will be what? X1. Then we do C5 and C2. That would be our C6 X3. And finally, we do it, we resolve X3 with, C6 with C4. And here we have, so we obtain empty clause, empty. So we canceled everything. And if we cancel everything, then that means the formula is not satisfied. Not set. Okay. So this is a principle of resolution. So let's check how it is done in our case. So, and by the way, so while being here, so as I said, this resolution is normally combined in algorithms in real solvers like GPLL or algorithms and such to first simplify a formula before kind of doing conditioning. So especially it works on so-called, I mean, in a way called unit propagation. So if you have some units that directly resolve to a single variable, so you can cancel the negated ones, and so by this simplify the formula first before conditioning. Yeah. Back to our example. So that was our initial set of rules. So the rules about the scenario rules, so to say, and the percept, or the fact, not percept. It is a fact since we are here in 1-1, so there is no poison. And also that's also describing our percept that we don't feel any smell. And now again, so our next move should be supported by this knowledge base, and we prove that we do not have P12. So we do not have anything here in cell 1, 2. So first, very briefly, I will not stand on each formula. So we do convert to. So we want to convert to CNF. We do the conditional elimination, blah blah blah. So you can read it offline. Yeah, and then you basically so using the facts that you have, so the previous rules that we don't have on this slide, you come to a conclusion. So and you insert it in your knowledge base that neither of the cells, either 1, 2, or or 2-1 or 1-2 has poison in it. And so it's safer to go there. And then, so what we can do again, so we can choose either to go in either direction. So we go here, so we filter set, and we add it to the knowledge base, and then the inference process continues basically. So maybe I can skip. So you can trace this. So you can trace this example at home, as well as the definitions. What I want to show is this. So this is a kind of already a simplified example of the reasoning by resolution. So when we have in the case where we have two rules in our knowledge base, and we want to prove that the hypothesis that there is no poison in the cell above us, and we do it by contradiction, as I said. So first, this is your knowledge base as a single formula. You convert it into CNF, so you can check this over the closest. And you negate the hypothesis and add it to the formula. And then you do the resolution is in a similar way as we traced on a simpler example. And as you can imagine, so for big knowledge bases, so this is also a complex process, computationally complex process, with, which actually also can be solved in non-polynomial time for cases where you have clauses with more than or equal to 3 conjunctions. So and here we come to classification or taxonomy of set problems. So you normally see such notations as 2-set, 3-set, k-set. And so the difference between them is the number of variables in the disjunctive clause. So with three variables, it will be 3-set, etc. And so modern solvers, they solve 2-set problem with only 2 variables in polynomial time, which is good, fast. And there is no polynomial time algorithm for solving 3-set and above. But modern solvers, they still do it quickly for rather large formulas, so with millions of parameters. So they solve it very efficiently. Mm-hmm. So while still being on SAT, I want to comment that that's a very useful problem in itself. So because many real-world problems can be formulated as SAT problems. Other usages of SAT. So many problems can be converted to SAT. Example, logistics scheduling. So basically, you have items uh, uh, to be delivered by trucks, uh, by number of tracks. No, not those tracks. To different cities or to different customers. To number of customers. Or an example of the same kind of problem is scheduling of classes, uh, uh, distribution of classes and or lectures in the classrooms. So over finite set set of classrooms. So and the general approach. General. So you first define binary variables. For uh, for the objects and relations between them. So, for example, x I would be schedule course A into pass P. And then you encode also in binary form encode constraints. Constraints. So and the constraints that no two courses can be scheduled at the same time, for example. So also in binary, I will give you a simple example. So um, no no two courses uh, are are in the same pass. Why? Because I mean these courses are taught by same teacher. And then here, so we can probably again see examples of constraints. Mm, Constraint example. For example, same. So that's a, I mean, same path. So if you have variables, so for um, x1, xn, constraint same would look like x1 and x2 blah 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 and xn uh, or and then negations x1 and not x2 not not xn or not same just a couple of instances not same. Here it's a similar looking form, but I mean you invert the operators. So x1 uh, uh, or x2 or xn and not x1 or x2. Uh, not xn. Uh, and in a similar way, you can, for example, define, again, for a set of variables, you can define that at least at least one is true. So you always you can describe it as a Boolean formal or at least k or less than k, exactly k. So that's that relations can be encoded in a Boolean formula. So find this information offline. So let's again trace a very simple example. So simple example. Um, so my case, I have two courses, and I ask our schedule office to schedule them. So LTE schedules courses. D7041E, so that my other advanced course, and D0034E. And we want to assign them to single teacher or same teacher. Not to confuse with the previous same teacher. So I assign to either pass 1 or pass 2, I mean, because of module placement. I mean, that's what we normally do. And uh, yeah, and then we have a rule again that each course must be in exactly one pass. One course, one And but at the same time, this one, rule one, and rule two, not in the same pass. So this is the problem to solve, and so we converted to SAT problem by assigning or introducing variables, Boolean variables. So x1 being true is d so D0034 E in pass 1 and x2 being false. So it's same course in pass 2. X3 same for the 7041E in pass 1 and X4 as false is the 7041E in pass 2. Right. And well, here is a made-up example. So it's I mean, we embed the first rule, so one course in one pass in the encoding of the variables. So so what we need to do, we need to ensure we need to encode the second constraint. So basically, it's not same, and so not same. We have seen it before. So it's basically x. So not same. So we have x1. What I always forget. It's or x2. And not x1 or not x2. And that is our SAT problem. So now we can take it and check satisfiability. So whenever we find assignment including to one, so we solve the optimization problem. So and again, so this is totally trivial example, but you can imagine. I mean, this logistic scheduling is a complex problem in general, but it can be so one way of solving them is yeah, converting it to SAT problem and solving it using SAT solvers. Okay, so and that is more or less it. So I think we are approaching the end. Yeah, that's true. What did we talk about over the past 2 days? Agents, remember? And so logical reasoning. So agents observe environment by percepts in the environment. There can be objects placed, and then you're able to describe these facts and put it in the knowledge base. And then in the case of propositional logic, so we use Boolean variables to describe these facts, and then we continued with the question of reasoning. What does it mean to reason? And so the main keyword here is entailment. So your set of rules should support the decision. So everything. So you can only say for sure when your knowledge base says yes, that's true, then I mean I agree that it's safe to go there. And technically, it boils down to model checking. So finding assignment of variables so that and checking that knowledge base is true. Which is a difficult thing to do with truth tables. So instead, alternative way of doing this reasoning and by converting it to a satisfiability problem. So first, and for this you need basically to convert it to conjunction normal form and solve it in one way or another, either by conditioning or by resolution. So, and there are ready-to-use solvers for this purpose. So, and that is it about logical agents using propositional logic. So, next, what happens next? So, first you read the book. So, book is very good. This is a classical classical topics you read in the book. So try different logical inference again. So you probably or most likely had this in the previous courses. Renew your knowledge. Do the test. So first quiz, and next week is a practice week. So you will start creating a knowledge base. So the week after, we will be talking about, it will be, I think, less busy week. So we will be talking about first order logic, we will be talking about fuzzy logic, and we will do an introduction to semantic web. So that's a totally different, so we will make a jump. So from classic logics to descriptive logic. So, and we will talk about also difference in the assumptions, like closed world versus open world assumptions. Okay, but that will come in 2 weeks from now. All right. Any questions, by the way? Okay, good. Yes. Yes. Just a second.